Welcome in. Our goal for this video is to describe our acids and bases using both the Arrhenius and our Bronsted-Lowry definitions, including the conjugate acid, conjugate base theory from Bronsted-Lowry. We can start with a quick overview. Acids tend to taste sour. They show up in a lot of foods. They can dissolve metals. There are ways to test for things that are acids, maybe blue litmus paper, or measuring the pH with pH paper or digital pH meters. Meanwhile, bases tend to taste bitter. They don't tend to be in many foods. They tend to feel slippery on your skin. They're good at dissolving oils. And again, there are ways to test for if things are basic using litmus paper or pH probes. We'll start with the Arrhenius definition. According to our Arrhenius definition, acids are compounds that produce H+ ions when they show up in water. In real life, when we produce this H+, really it's going to grab a water molecule and stick to it. So what we see in real life is H3O+, and we call this hydronium. Throughout these videos, I might use H+ and H3O+ interchangeably. H+ is a nice shorthand, whereas H3O+ is maybe more realistic to what's actually happening in our solution. Regardless, our acids produce this H+ or hydronium when mixed with water. Bases, on the other hand, are compounds that produce hydroxide, OH-, when they are mixed with water. We have some examples. HCl is going to be an acid. It will dissolve and produce some H+ ions as well as some chloride. Whereas our sodium hydroxide will dissolve and produce that hydroxide as well as some sodium. It's the fact that we are producing these H+ and OH- ions that makes these compounds acids or bases, respectively. We can take a look at this visually as well. Here we have HCl and NaOH. What actually shows up in our beaker are these individual ions. So HCl completely reacts and decomposes into chloride and H+, whereas sodium hydroxide completely dissociates into sodiums and hydroxides. We can move on to a second definition of acids and bases. This one is going to be maybe just a little bit better, a little bit more inclusive of a definition to capture all of our compounds or more of our compounds that do behave as bases and acids. Our definition for acids is now that acids donate protons or donate H+ ions, and bases are going to accept protons or accept H+. If we have H+, remember the number of protons depends on the element. So since it's hydrogen, it always has exactly 1 proton. Most of our hydrogens have exactly 0 neutrons. And if we formed a +1 ion, that means we've lost one of our electrons, and now we are down to 0 electrons. So Arrhenius was talking about H+. Well, we can see that H+ is really exactly the same as a proton. And in terms of how it interacts with water, it will really exist as H3O+. These are all kind of equivalent ways of describing what's happening. H+, a single proton, H3O+, all thinking about the same idea. We have a couple of example reactions. We can try to look at what's going on and keep track of how these H+ ions, how these protons are moving around. to go from HCl to Cl minus, we have to get rid of that hydrogen ion. We change the number of hydrogens and we change the total charge. In other words, for HCl to turn into Cl minus, it has to be an acid, losing that H plus. In this Bronsted-Lowry kind of scheme, if something loses that H plus, it has to go somewhere, and so something will be also gaining that H plus or accepting that H plus. Here, HCl handed the H plus over to water, so water has to be our base. And this is going to be typical. We're going to have a Bronsted-Lowry acid reacting with a Bronsted-Lowry base. In our second example, NH3 ammonia is turning into NH4 plus ammonium. In order to do so, it has to gain or accept that H plus. Because of this, our NH3 is acting as a base. That H plus has to come from somewhere, and in this case, it's coming from that water. Or in other words, water is our acid reacting with ammonia, which is our base. You might have noticed that water was a base in our first example, and water is an acid in our second example. We call this amphoteric. It can be both an acid or a base, depending on the context, depending on what else is around it. Or it can even act as an acid and a base when reacting with another one of itself, as we see down in our third example. Our last concept that we want to introduce is this idea of conjugates. We looked at the reaction between NH3 and H2O, and we said that ammonia, NH3, is a base, while H2O, water, in this case, is acting as an acid. We can also look at the reverse of that reaction. If we are starting with the other side, starting with NH4 plus, combining with OH minus, we can go and we can build back what was originally our reactants. This is what that looks like. We have NH4 plus combining with OH minus, producing NH3 and H2O. If we're doing that backwards reaction, we can also describe things as acids and bases. In order to do this reaction, we need to send the H plus away from ammonium, NH4 plus, and onto that hydroxide, OH minus. Because of that, NH4 plus is acting as an acid. OH minus is acting as a base. If we think about what we drew on the previous slide, we said that NH3 was turning into NH4 plus, or in other words, something that was a base, NH3, turned into something that is an acid, NH4 plus. We can also do this with our water and our hydroxide. Water turned into OH minus. In this reaction, water acted as an acid, and it turned into hydroxide, which was acting as a base when it was doing the reverse reaction. We call NH3 and NH4 plus a conjugate acid-base pair. We can also call water and OH minus a conjugate acid-base pair as well. This is going to be two molecules that are only different by adding and subtracting an H plus. We can also see that one of these is a base and its pair has to be an acid. And finally, when we have this full written out reaction, one of them is a reactant and one of them is a product. They are on opposite sides of our reaction arrows. This is our Bronsted-Lowry conjugate pair. One acid, one base, only different by adding an H and adding a charge, or subtracting an H and subtracting a charge. And if you write out that full reaction, one of them is a reactant, the other one is a product. Your base turns into its conjugate acid, or your acid turns into its conjugate base. Here is another way to picture this. Now we are looking at the actual molecules. NH3 turns into NH4+. Oh, they're only different by adding that H+, or subtracting an H+ if you're going the other way. Meanwhile, water and hydroxide are also a nice conjugate pair because they're only different by adding or subtracting H+. We have a couple of reactions, and we're asked to identify our acids, bases, conjugate acids, and conjugate bases. Let's look at this first one. Can we keep track of where our H+ is moving during the process of this reaction? It looks to me like H2O has to get rid of a hydrogen and C5H5N has to gain a hydrogen. If that's the case, water is acting as our acid. And C5H5N is acting as that base. To think about our conjugates, we want to look at the other side of our reaction. Our base is going to turn into the acid. So our base was C5H5N. Our acid has to be the one that is so close to that, only different by adding a hydrogen, adding a charge. There we go. On the right side, we have our conjugate acid. If we want to identify our conjugate base, well, our acid on the left side will turn into the conjugate base on the right side. It turns into that conjugate base by removing that H+. It must be our hydroxide that acts as that conjugate base. We have one more problem here for practice. We'll leave that for you. Grab some paper, grab a pencil, try to write down that good answer. With that, we have accomplished our objective. We can describe acids and bases using the Arrhenius and Bronsted-Lowry definition, and we know all about our conjugate acids and bases. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.